Welcome to another podcast. In this episode, we're going to be taking a look at homogeneous equations. And I don't want you to confuse this with linear homogeneous equations. This is just a class of differential equations which are called homogeneous. A homogeneous equation, at least in the first order case, is any differential equation which can be written in the following form. Basically, it's the non-derivative part, or the right-hand side of the differential equation when written in this form. That is a function, an arbitrary function of y over x. So this is called a homogeneous equation. Not homogeneous linear, but just a homogeneous equation. To show you an example of this, if you've seen the video on Bernoulli equations, the differential equation that was seen in that video is actually also homogeneous as well as being Bernoulli. Let me remind you of what that differential equation looked like. It's 2xy dy dx was equal to 4x squared plus 3y squared. And what you can see here is that when you take and divide by 2xy, you will obtain the following. And with some clever algebra going on here, we can actually rewrite the right-hand side as being 2 over x divided by y, plus, you can see here, you get 3/2, and then there's that y over x term that pops up. Now, just one more small change to make. I'm going to convert x over y to y over x inverse. And you can see here that the right-hand side of the differential equation is a function of y over x, as was indicated as the form of a homogeneous equation. I think the substitution here is probably obvious as well, but if you're looking to solve one of these differential equations, the substitution that you need to try is let z, the substitution variable, vary as y over x, which means that you will end up with y being equal to z times x. And if you want to differentiate that, which you'll want to because you'll want to substitute in for dy dx, it turns out that dy dx is, if I take, because z is a function of x, if I take a derivative of this product, I have to use product rule. So this is going to involve both product rule and chain rule. So you might want to bone up on those things this semester. But dy dx would be equal to, in this case, I'll start with the derivative of this with respect to z. If you take the derivative of this with respect to z, you just get x, plus if you take the derivative of this with respect to x, you get, did that backwards. If you take the derivative of this with respect to, I did it right. If you take the derivative of this with respect to z, then what you will end up with here is, if you take the derivative of this with respect to x to start out with first, then you'll wind up with just z. Because the derivative of x is 1, you get 1 times z. Now you have to take the derivative of this with respect to x, but you're going to take the derivative of the z part with respect to x. So if you take the derivative of the z part with respect to x, then that's going to be wind up being x times z prime, or we'll just say dz dx. So this is a basic product rule and what it would look like in this case. Basically, it's the derivative of x, which is 1, plus x times the derivative of z. So these are the substitutions that we'll use, and it turns out that when you do a substitution on a homogeneous equation, this becomes separable post-substitution. And that's one of the things that you'll verify on the homework, is that the substitution z equal y over x will transform a homogeneous differential equation into a separable one. And so I want to take a look at an example of that. Suppose we are looking at the differential equation x dy dx equals y plus the square root of x squared minus y. Okay, in this form, I would suggest trying to write it in standard form, or push everything over to the right-hand side like we did here to verify that this is indeed homogeneous. So we're going to get dy dx is equal to y over x. There's our first good sign, plus the square root of x squared minus y over x. So I'm going to manipulate this algebraically to be dy over dx equal y over x. I'm going to bring the x inside the root as an x squared. And when I do that, you can immediately see what's going to end up happening for this particular problem. And my apologies, I've left off a y squared here. This should be y squared, y squared, y squared. So you can immediately see what's going to happen here. Our differential equation will turn into y over x plus inside the root is x squared over x squared is 1 minus y squared over x squared is quantity y over x squared. So we have verified that this is indeed homogeneous because you can see here that wherever there's a variable, the variable is of the form y over x. And so if I do my substitution now, then this differential equation, I can replace dy dx with this. I can replace y over x with z, and it will occur in both positions, so that the differential equation, the z's, will cancel with one another. And we end up having the following differential equation, which should immediately be recognized as being homogeneous. So if should immediately be recognized as being separable. So if I separate z from x, then I end up with the following separation of variables. And we know at this juncture the next step is to simply integrate both sides. Doing so will give you, you may or may not remember this, but this is a pretty common antiderivative from Cal 2 or the end of Cal 1, depending on when you saw it. 1 over the square root of 1 minus anything squared is the arc sign, or I'll say the inverse sign of, in this case, z. And that's equal to the natural log of x plus I'll introduce a constant of integration. So I'm going to solve for the variable z because that's my substitution variable by taking the sine of both sides. And when I take the sine of both sides, I can get at z easily, but I need to go back in terms of the original variable. The original variable here is y. So I'm going to replace z with y over x. And then finally, I'm going to obtain an implicit solution or an explicit solution by multiplying through by that x. And so what you'll notice is we have arrived at the final solution, y as a function of x, for this differential equation. And so this is typical of a homogeneous equation. You'll be able to write it in the form as an arbitrary function of y over x, just like we were able to do here. And once you've made the substitution y over x, you can reduce this to a differential equation which is separable, just as this one was. This is a separable first order ODE. We separate out the z's from the x's, and once we do that, we will solve for hopefully an explicit solution, but it might be an implicit solution for the dependent variable, which in this case for the original problem was y. All right, thank you for watching.